Hello again. Tonight we're going to talk about a paper that was released back in April of this year about space-time having three dimensions of space and three dimensions of time. And two of my favorite YouTube creators, Anton Petrov and Sabina Hassenfelter, did different views on this paper. And so I'll give kind of a third view of it. So here's the gist of it. The name of the paper is there, where it came from, when it was released. There's a link at the end of the presentation. But instead of time having just one dimension, he postulated or conceptualized that time actually has three dimensions, one of which is for measuring mass. That's the quantum scale. One of which is for measuring quantum effects at very small levels. That's the interaction scale. And another one is for gravitational waves, and that's the cosmological scale. We'll get into why three different scales for three dimensions of the same value. So I looked over Anton's presentation. It was his usual analysis, asking questions, but never really questioned whether or not this thing actually exists. Sabina was more to the point. Apparently, early on in her career, she thought this way, that why does time only have one dimension? And then after taking a lot more physics, and she realized that doesn't make sense, and went with the known information. But in order to put forth her point, she attacked the paper, the author, the publication, sprinkled it with profanities to try and drive home her point, and said that the paper should have never been released. But she didn't do it in her normal, sponsored, well-presented way. She did it kind of like leaning into her desk surface. No, Sabina, tell everyone how you actually feel about this paper. So I get a little humor out of that. So I watched both those videos and then went looking for the paper and found out, oh, I'm not a part of that group, so I can't download the paper, but I can scroll through it and read parts of it. Now, I didn't read the paper in its entirety because I wasn't able to, but I did read parts of it. So I think that both Anton and Sabina missed the mark, and they missed something. So I'll bring a third thought on this paper. So for those that are aware of particle physics, there are things that still need to be understood better and explained. And some of this surrounds neutrinos, and some of this surrounds why things move at the velocity that they do. Electrons are considered slow by comparing it to the speed of photons, and photons are considered a bit slow compared to the speed of neutrinos. So why is that the case? So there's some things left to discover and prove out in physics. Now, this paper is not proposing any new laws of physics. It's just conceptualizing and conjecturing some things that maybe if you follow the math that they're proposing, the numbers will come out better. And it turns out some of the math that they've done does make numbers that come out to be not exactly the same as the standard model, but certainly within a statistical ballpark of the standard model as to the mass or energy of things like neutrinos. It's a conjecture on their part, but you need further research by others doing peer review, reproducing observations, and then analysis, and they come away with the conclusion, do they agree this carries any weight or disagree? And we'll get to why that might not happen. So I'm going to run through this quickly because most of you know me, and I do post a page at the end of each presentation to explain the soapbox upon which I stand. Basically, I'm not a particle physicist, so what I know about particle physics is from my physics classes in college, and I've self-taught myself on a lot of topics. Or as Ben Franklin, I think, once said, he was self-taught hath a fool for a teacher. But then Ben Franklin taught himself a lot of stuff. Not that I'm a Ben Franklin, but analog point. My not recorded stuff might have some profanity in it, but I try and keep the recorded stuff clean. So to me, there's a difference between critiquing something and criticizing it. If you're attempting to understand the quality of the content of a certain paper or analyze it, then I think of that as critiquing it. And your critique should include information about the paper, where it came from, when, links to it, that kind of stuff, and maybe identify yourself, the soapbox upon which you stand, so we know, whether your opinion might have any weight or not. You can make statements. I don't believe this is the way that particular aspect of physics works. You can ask questions. Well, if you're stating this, then what about that? You can do those kinds of things. You can offer alternative points of view, like, well, I think you've almost got it, but maybe consider doing this. So critiquing it. Typically, you'll exclude judgments regarding the author, the institution they work for, and the publication or the journal in which it was published. You're not there to cast doubt on things. You're there to analyze what was presented. Criticizing, I see, is different. You might think of a critic as someone who watches entertainment and then gives you their opinion. I think of criticizing a scientific research paper as basically propping up your personally held belief or disdain for the content. And you should, avoid disdain as a means of propping up your personally held position regarding the author, their institution, or the journal. And definitely don't use profanity to try and empower your statements. It's not truer because you said it's effing truer. A truly strong critique will stand on its own. You don't need a lot of personal attacks and such. I don't think maybe a personal experience is a way of describing your soapbox, but it shouldn't be included as part of the critique presentation. Of course, the offline, BSing discussions are a totally different topic, and you can mix critique and criticizing in those scenarios, but it's pretty obvious which one's which. Why do things have multiple dimensions? Because they need them. If you think of space as having 3 dimensions, why does it need 3 dimensions? If space were just made up of points, then you don't need dimensional measurements. It's just a point, and a point has no dimension. A line, the moment that you come up with a line has a linear length. You have to measure the length of it. If you're measuring that line in 3-dimensional space or just even 2-dimensional space on a surface, you need angles to say which way the line is pointed. The moment that you join 2 lines with a point, you now have 2 lengths that you have to measure and an angle separating them. And then if the 2 lines joined by a point are rotated around in 2-dimensional or 3-dimensional space, you need those angles as well. The moment you start making 2-dimensional polygons, something simple like a triangle, you need more lengths, more angles, and if you orient the triangle in 3-dimensional space, more angles. As soon as you get to a 3-dimensional object, let's say a pyramid or a cube or something like that, you add another dimension, depth. You need all these dimensions to describe what you're talking about so that others can reproduce it, analyze it, and so you can communicate this thing you're describing to other people and they can reproduce it. So you need measurements of each of these values so that you can describe something. Here's something worth noting that will come out in the paper. When you have multiple dimensions, they'll reuse the existing measurement units. So if you have to measure multiple length, you might use different units of measure, like inches or feet or meters or whatever, but you'll use the same unit of measure for each of the linear dimensions that you're making. You won't say like, I'm going to measure X in meters and I'm going to measure Y in fortnights. Well, you could, it's a length, but it doesn't make sense to do that. And angles, whenever you're measuring inside angles, outside angles, or rotational angles, the angular measurement doesn't change with the dimension. So you don't say like, well, in the X angle, I'm going to use degrees, and in the Y angle, I'm going to use days. It doesn't make sense to use different units of measure for different values in the same quantification. And standard units don't change with dimension. So if I said, I'm going to measure X in meters, and a meter is based upon this standard value, but in Y, I'm going to measure in the thing I call meters, but it's based upon a different standard value. So you don't change them based upon which dimension you're measuring. To our knowledge right now, space has 3 dimensions, height, width, and depth, or X, Y, Z, if you're measuring them from a point of reference. There are other theories, such as string theory, that require many more dimensions, both in space and time, but no evidentiary data to prove all the aspects of string theory at this point. So it's just a theory. But for the moment, we have 3 dimensions of space and 1 dimension of time. The definition of the units of measure don't change with the dimensions. If I'm measuring X, Y, and Z in meters, I don't change the definition of meter to fit X or Y or Z. It's all the same. Time, as we know it right now, has 1 dimension. Time has 1 dimension, and that is length, or basically the point from some point in time to another point in time, and there's a progress along either a line or a curve if you've got a lot of gravity, and the progress can change, but the time itself, that unit doesn't change. It's still linear. It's from one time point or t point to another. So does time need multiple dimensions? Well, if we had things that we needed to measure in time, then maybe time needs multiple dimensions. It's unlikely that it needs different units of measure because we have plenty of measurements of time. But the actual dimension of time, we only have one dimension of it. But this paper is conceptualizing time as needing three dimensions in order to basically bring together the various aspects of physics. Now, you've probably heard of the classical joining of the fundamental forces, the strong force, the weak force, the electromagnetic force, and the gravitational force. And yes, that's still something that science needs to deal with, but it's not urgent to do it right now because all that we know about the various forces does seem to work in practice. This paper was referring to it as T1 refers to mass. And if you're into studying physics, you'll know that mass is just a way of measuring energy. And then T2 is quantum. Quantum is not really a measurement. It has multiple measurements, forces and distances and times, but it itself is not one dimension. And then you have gravitational or gravity waves. Gravity waves move at a certain speed, and that's measured versus the speed of light. But there aren't multiple measurements for it. There's one. So by leaving out some of the forces that we know of in the quantum category, they've combined it all down into one called quantum, where they're T2, and adding something that they didn't understand as a member of quantum when quantum is multiple measurements. That seems a little odd. And were they really just trying to get three dimensions for time to match the three dimensions of space? Did they kind of cook the books to get the number to come out to be three? I don't know. I can't speak to that. So if time were actually branching out and we could measure it in different directions, different dimensions, then it might be justified to add additional dimensions to time. But so far, we've not seen that. The multiverse is not something that we have physical confirmed evidence for, but we do know that time in the presence of high gravity can be affected. We do know that some things move faster than others, so there's a velocity of progression that varies with certain particles. So for this concept in this paper to be valid, you would need to change the units of measure, basically the standards for measurement based upon whether you're measuring T1, T2, or T3. Mass is typically measured as electron volts because we can convert that back to a force, which we can measure as mass. Things in the quantum world have multiple effects that they use different units to measure: distance, energy or mass or force, and duration of time. So quantum is not just one measurement, it's multiple. And then gravitational waves propagate in velocity relative to the speed of light in meters per second or miles per second. So having different time dimensions or having different standard units be different for different measurements doesn't follow suit with what we know about dimensions of space. You'll often hear this when you're analyzing a research paper: does this conjecture or this postulation have legs? And what they're really saying is this conjecture sufficiently grounded in known science? Does it follow the rules, so to speak? If it's a conjecture, is that an extrapolation based upon the rules? Is it taking the rules, connecting the dots, and showing something new that's been learned? If it doesn't have these legs, then it's very unlikely to get the funding from the people that hold the purse strings to do any future science because it's not mainstream enough. It's too bleeding edge, too fanciful, not well-founded in known science. The two things that kick the legs out from under this paper is not fully recognizing all the currently recognized fundamental forces and using different units of measure for different time dimensions across the three different dimensions of time. So I'll just state it as it's going to be hard to get funding for something that doesn't have legs. So here's my take on that. The paper and the presentations is it's just a nag on my part. Fundamental forces eventually require unification, not immediately, but eventually. just not yet, but I don't think this paper solves that. The next thing that might help that is if we ever created the technology to measure a graviton as a particle of gravity. We don't have that technology yet, so it's just a nag. Eventually, we'll unify them. So one of the things that was put forth in this paper is we don't have a good explanation of the different rates of propagation of electrons versus photons versus neutrinos. And I know that there's already a solution for that, which is they travel at different rates based upon the velocity when they're emitted and the different levels of interaction, absorption, and re-emission of the various types of particles, and then the medium in which they travel. Do they travel in a vacuum or not? When they're emitted, are they emitted at the speed of light or at something less than the speed of light? As they travel through something and they encounter other particles, do they interact with them? Are they highly interacting? Are they absorbed and then re-emitted? We know that to be the case for photons. But in the case of neutrinos, they're very weakly interacting. So I could say that, electrons move slower because they're more interacting than photons, which do interact if the right material is present at the right energy levels, and they can be absorbed and then re-emitted. Whereas neutrinos, if they're moving through pretty much the vacuum of space, they're going to move the fastest. But we do have mysteries associated with neutrinos. The precise energy of all the flavors, we currently believe there's 3 flavors of neutrino, and that seems to match up with having, oh, look, we have 3 flavors of electrons. Is that another one of those? Well, we have 3 of these. Why not 3 of those? Well, we've only seen the 3, and they're electron neutrinos, muon neutrinos, and tau neutrinos. But if you notice in the picture down at the bottom, they're all less than a certain number of electron volts per the speed of light squared. The reason why they're less than is the numbers vary. Not only do we have 3 different flavors of neutrinos, they each have energy or masses that we don't have an exact number from them. They're in a kind of a ballpark. So we know that they're not greater than these values, and that's how you separate electron from muon from tau, because notice they're all 0 and 1/2. They're all neutrinos. They're all weakly interacting. They're all neutrinos, neutral. Is time 3-dimensional? Personally, I don't think so, particularly if it requires different dimensions to be measured differently with the same units. So here's the summary. Here's my takeaway from it. Space has 3 dimensions, x, y, z akin to width, length, and depth. Time has only 1 dimension. That's the progression of time. Of course, that's just my opinion. As they say, opinions vary. What do you think? Here's the soapbox. And then links. I always bring the links. Okay.
Hi, this is Joanne.
Hi, Joanne.
I have a question.
Sure.
I think last week I talked to you about multiverses and trying to come to some kind of thought about it. Now I have a thought of this time. And did just one person trigger your thought on this, or did you get many different directions for this time thing? Because I'm wondering how many people think that something else is in time, that time's linear. Are we talking about time travel? Is that what spurs us on, that people think that we could travel through time? Or
no. This was a research scientist at the University of Alaska in Fairbanks. He was the lead author of this paper. There's a couple of other people that are on the paper. He was conceptualizing and saying, if space has 3 dimensions, why does time have only 1 dimension? If we can come up with a mathematical model for time involving 3 dimensions, and then we run the numbers, do the numbers come out to be the same as those found in the standard particle model? And as it turns out, they've made the mathematical formulas such that if you were to have space have have time have at least 2 dimensions, then some of the numbers that come out of that do closely approximate like the masses of neutrinos. But since we don't have an exact number for the mass of neutrinos, we just know that each neutrino type is less than a certain mass. It's probably not unusual to be able to create a mathematical model to do that.
But my question is that I can say space has 3 dimensions. So, a ruler has, I'm not saying you can't equate that because, or maybe you can. Maybe there's some kind of scientific thing out there that says because space has 3 dimensions, time should have more than one. I don't see how they relate. I don't know why he could just bring up time,
Well, that
one direction. We have more than one time.
that was one of my statements in the presentation was
Oh,
space has 3 dimensions. Did
right.
you find a way to kind of cook the books to make time have 3 dimensions so you'll have 3 of space and 3 of time? Because there's a number of the string theory postulates that say time actually has 2 dimensions. This guy's saying, well, because you've got 3 of space, maybe you should have 3 of time. 3 and 3. You're like, well,
But in his paper, he's not actually proving anything. He's just right. Okay.
No, it's conjecture.
Okay.
Just conjecture.
Okay.
And so that
He did have a mathematical model that he put forward that I don't know whether he came out with the numbers that he wanted and then converted back to the math that he did. I don't know enough about him as a researcher, but I'll just say, I'm going to ignore his mathematical model. I'm going to ignore his shoehorning quantum, which is multiple measurements into a single measurement, and just say, well, it would be very weird if, let's say, we were measuring physical space and we measured X, Y, and Z, and we called all of them as being measured in meters, but we had a different standard for meters in X versus meters in Y versus meters in Z. And that's what he's literally doing is saying, we've got 3 dimensions of time and we're measuring each of them as dimensions of time, but we're using different standards for each of the dimensions. That doesn't fly with me.
Okay. Now, what about the fact that you're saying, or I don't know if I heard it correctly, but you're saying this is this guy's theory with the three time dimensions, but you did say something about there was somebody out there that proposed 2. Do we believe that there's 2 dimensions? I know you don't. You believe that there's only 1 dimension.
Right. There are string theorists, and their theory, because we have no evidentiary data, no observations to prove it, that there's a certain level of string theory where they state that time has multiple dimensions, not just one. And there's a couple of aspects of string theory where time has 2 dimensions. I'm not a string theorist, so I can't speak to the details of that. I'll just say that there are other people out there researching that will state in theory, conceptualizing, that time has more than 1 dimension. Remember what I stated about space. The reason why we have 3 dimensions of space is in order to describe something, we need 3 dimensions, X, Y, and Z. So in time, if there was really observations that said time moved differently, then maybe we could say, I need more than 1 dimension of time. And I think that's what the string theorists are saying is because of gravitational effects, time moves faster and slower. But I don't see that as different dimensions. I see that as just a different progression in the presence of gravity.
Well, also, like you're out in space, your time is slower than when you're on the planet Earth. But I also
not because you're out. That's not because you're out in space. That's because you're out in space, moving at a high velocity.
Yeah. Okay. Exactly. But what I'm saying is that's based on the same thing about the moving of the vehicle. I don't see that. I see it more like you see it. I don't see it that
it's a rate of progression. It's not a different dimension.
Right. Right. But so, they're thinking that that's a different dimension.
Not exactly. They're just saying we have these kind of unknowns in physics involving quantum and neutrinos and gravity and mass. And if we come up with a new approach and say each one of those is a different dimension of time, does that join together the separate camps of physics?
Well, the quantum, the ability of being in the same place at the same time where we haven't ever thought of something being in the same.
No, there are actually rules of physics, right? Laws, but rules of physics that say no 2 particles can be in exactly the same place at the same time with the same energy level.
Right. But we're saying with neutrinos and stuff that they're going on different levels and that you can do it sort of.
No. No, neutrinos are just very weakly interacting particles, and they can, a neutrino can pass through the entire Earth or pass through your body, and it never interacts with any of the particles in your body. So you don't know that right now 50,000 neutrinos per second are passing through your body, but they are.
Right.
You know,
I mean, I come to conclusion to understand that.
well,
I can't like you say, I can't picture it, I can't imagine it, but you've said it several times, and I've come to the conclusion that, yep, that's probably happening. Those neutrinos are going right through me right now as Monroe's talking to me.
well,
And what are they doing to me? Who knows?
Yeah, we're also getting radio waves going through us,
yes, what you don't know that doesn't hurt you is unlikely to hurt you. So radio waves all around us don't seem to hurt us. Neutrinos passing through the earth and passing through our bodies and everything doesn't seem to hurt us because they're not interacting. So don't worry about it.
They're doing, it's like, why have all these neutrinos going through us for no reason at all? I mean, the radio waves, at least we know they're doing something.
Okay, let me give you a brief synopsis of what neutrinos are there for. When they were studying how fusion works and how stars work, the math didn't work out right. They said, so when this supernova occurs and the star explodes, it's not all matching. It doesn't all come out to be, the amount goes into doesn't match the amount goes out of, and they had a little left over. And so they decided, well, what's left over doesn't interact. It's weakly interacting. So they came out with this, maybe there are these things called neutrinos that are weakly interacting that fill the gap for when a supernova occurs, and now all the math comes out right. And as it turns out, kinda, it's a lot closer. Neutrinos were postulated to exist before they were ever discovered.
Right. Okay.
And then by having a giant vat of dry cleaning fluid, and then having neutrinos pass through it, the very weakly interacting became very mildly interacting. And occasionally you would get a little photon of light that could be measured in your vat of dry cleaning fluid.
Wow.
And that's actually confirmed the existence of neutrinos. Now,
Wow.
since then, we've created other sorts of neutrino observatories, they're called. And, we filled giant vats with salt water. We've put a bunch of sensors in the Atlantic Ocean. We've buried sensors in ice in Antarctica, thousands of them. That seems to be pretty successful, is if you have extremely low light sensing that they can measure the, not color, but light amplitude, the energy in photons. If you suspend a lot of these things down into very clear, pristine freshwater ice, then when a neutrino passes from the North Pole through the Earth and comes out at the South Pole, you can probably detect the rarest of light particles. And if you have enough neutrinos due to a supernova going off somewhere, you can get enough neutrinos that you can actually measure a spray of photons from the weak interacting neutrinos. And therefore, you can roughly calculate the direction of where those neutrinos came from, and then go look in the sky in other wavelengths of the electromagnetic spectrum and go, that was a supernova. We just didn't know it was there. That's kind of how we found neutrinos, and they are very weakly interacting, but not 100% not interacting, just very, very low probability.
Thank you.
So that's how they can pass through us all the time, and we never even notice it. Plus, they're also very small, and even if one did affect a cell in your body, you probably not even notice the molecular issue in your cell, or you're probably going to recycle that cell in your body and spit out another cell through division. And again, you'd still never notice it. Now, X-rays and gamma rays, that's different.
Yeah.
Because those are high enough energy and those are interacting that they can actually damage your DNA and induce cancers. So yeah, it's not like X-rays and gamma rays.
No. But so we're back to the time thing.
Yeah.
And you're saying there's people out there that believe that there's two dimensions to the time.
Those are string theory.
And the string theory. And I'm trying to figure out what is that other dimension if it's not with the quantum in the same near space, which we have had saying you can't have two things at the right until, well, never mind my thoughts about that. What my thoughts are is what is showing up as the second dimension, or do we know what they think the second dimension is?
Well, that was in his paper. He has 3 dimensions that he's described. The string theorist, he didn't describe that in his paper. That's in separate string theory papers. And the premise of string theory is that it will involve additional dimensions beyond just 3 of space and beyond 1 of time. And we do not have any current technology, nor in the foreseeable future will we have the technology to be able to observationally confirm string theory. And to me, that's like, okay, you're telling me no matter how much money we spend, we won't be able to observationally confirm string theory as you've currently theorized it. So yeah, I'm not going to waste a lot of time on that.
Yeah, they try to prove it with the mathematics, but not
Yes.
experiment.
And the funny part about string theory is the number of dimensions they need to prove it out. String theory originally said you're going to need 4 dimensions of space, but that didn't completely explain it all. The math didn't work out right. Okay, you're going to need 5, 6, 7, 8, 9 dimensions of space, and it still didn't work out right. And so they said, okay, it'll be 10 dimensions of space. And people were like, okay, fine, we hear what you're saying. And then they said, well, it's still not quite right. We're going to need 11 dimensions of space. And that's where the string theorists broke camp. And they said, there are the lesser dimension count string theorists and the open-ended count, dimensional count string theorists. And I said, well, when you guys create some technology that allows you to observe and start to confirm some of your theories, or the math works out to the nth decimal place, then I'll pay more attention to string theory. But in the meantime, I'll just describe it as it's string theory.
Yeah. Thank you.
Okay. So like I said, I just watched Anton's video and Sabina's video, and I thought, you're leaving out the elephant in the room or the bear in the room or the gorilla in the room or whatever. Units of measure, if you have a standard for it, if you say this is the meter and the meter is defined by time of speed of light. Okay, you got a standard for the meter. And then you said, okay, when you're measuring the meter in the X direction, that's the meter. When you're measuring the meter in the Y direction, the definition of a meter changes. And then when you're measuring in the Z dimension, the definition of the meter changes. That don't make no sense to me.
No,
That's what he's saying is these 3 dimensions of time have different measurements, but they're based on the same unit, which is time.
No, doesn't make sense.
But I'll let somebody else. Sabina really I've never seen her so profane in a single presentation.
Really? That's
Yeah.
amazing.
Really?
And she didn't do it from her normal, like, nicely dressed, hair done, makeup, professional production with a sponsor. She just basically was at her desk and leaned into the camera in her, like, day-to-day wardrobe with her hair all like.
Oh,
It was
wow.
very unlike her. She very much didn't like this paper, and she stated it should have never been published.
Wow. That is really,
So if you're into watching her, the link's at the end. It was in the email. That's
interesting.
Monroe, have you seen, I suppose you've seen the Australian mathematician who has the Tibby's YouTube channel that's mostly about 1-dimensional, 2, 3, and 4 and 5-dimensional creatures?
no, but I watched the Doctor Who episode called Flatliners that described the world as if it was 2-dimensional, not 3-dimensional, and how if there's a bleed over from 2-dimensional beings to 3-dimensional beings, how that might take place.
Yeah, well, I'm only surprised because we usually get so similar things on our feeds. But I just sent just how different a 4-dimensional creature would see something.
Yes.
It's really interesting because what she always does is she says, well, here's how a 2-dimensional creature would see it. And you look and say, yeah, wow, they wouldn't see that. And then extrapolates it. I just sent you a short on your messages. It's like 90 seconds. Do you think you can play that?
Do you want to take off recording?
Yeah, I'll take a recording and stop sharing to make it easier to do that.